All right, so here is this infinitely long charged wire, positively charged, and it has linear charge density lambda. We know lambda, and I want to find the electric field at a point a distance r away, and we know r. All right.
Now, this is super easy using Gauss's law, but maybe you don't know Gauss's law or you're a masochist or something. So let's use integration. Let's just brute force this thing and integrate to find out what the net electric field is due to this charged wire. Okay, let me shrink that down a bit there so I have some room. Okay, so we know we're looking at an integration problem, so what we need to do is pick a representative piece of what we're looking for. So what we're looking for is the net electric field. So if you imagine this little piece of charge right here, this tiny piece of charge, I'll call it dq, that would cause this tiny piece of electric field, dE, right here. And then another charge would cause a different piece of electric field pointing in another direction, and so on. So one of the first things we have to watch out for is the fact that we can't just integrate the electric field equation, because electric fields are vectors, right? So if we added them all up, we'd be adding, this one and this one and this one, and it doesn't make sense to add those up because they're pointing in different directions, right? You don't add vectors like that. But if we use a bit of symmetry, we can realize that all of the x components of electric field are going to cancel out. And if you want to think about it, same thing with the z components, which are pointing out of the screen at you. So the only thing that we're going to be left with in the end is an electric field pointing straight away from the wire. All right, so make sure you understand that reasoning. So we'll be adding up every little piece of y component. If we just add up all the y components of dE, then we'll be good to go. That will be the answer. All right, so this forms a little right triangle here. Maybe I should have dotted that, whatever. We don't care about the x components, but if you look at these two right triangles, here's a right triangle, and here's a little right triangle in the electric field. This, oh, let's see, I've got to define the coordinate that points to my dq, right? So that points, defining the coordinate that points to my dq, oops, we'll call it x. This will be the x-axis. Right here will be the origin, and x points at dq. So that makes this hypotenuse of this triangle the square root of r squared plus x squared. Now I'm curious to find DEY because I want to find EY in the end. So if you look at these similar triangles, DEY over DE is equal to R over the square root of R squared plus X squared. Okay? And multiply over the DE, and that's how we're going to pick out our fraction. That's how we'll determine DEY given DE. Okay, so let's figure out what DE is. Well, DE, this is electric field we're talking about. So since we're imagining this tiny little piece of charge, we can just use the, it's not Coulomb's law exactly, but it looks like Coulomb's law. That's where you have the charge over 4 pi epsilon naught r squared. All right, so that's the electric field due to this charge dq at a distance r away. Although this r, I just mean as the general r from this equation. What it means is the distance from the point to the charge, and that's actually r squared plus x squared. So r is equal to the square root of r squared plus x squared, and so r squared is equal to that. All right, so that's what actually goes in our equation. dE equals like that. Okay, so that's dE. We mentioned before how we can get dEy, right? So dEy is equal to r out of square root of r squared plus x squared of dE. that. And that can be rewritten to the 3/2 power there. Because this is to the 1/2 power and this is to the 1 power. Okay. So now we're getting ready to integrate here. Now because our dq is moving along the x-axis, right, in order to integrate across all q, we're moving our dq along x. Well, our integral is going to be with respect to x from negative infinity way over there to positive infinity. All right, so let's prepare for that. So ey, which is what we're looking for in the end, is equal to the integral of dey, or in other words, the integral of all this stuff. Okay, but I just mentioned that we're trying to integrate across x. So we need a dx to be in here, right, in order to integrate across x. So we need to somehow figure out how to turn this dq into a dx. And the answer is the linear charge density. Remember, in general, linear charge density is total charge over total length, right? But for something with a constant, just a uniform linear charge density, which this rod is, I don't know if I mentioned that, it's also true that any little piece is over the little distance that corresponds to it is equal to the linear charge density as well. So let's see if I can get everything on here. So this little piece of dq is at length dx. And so our linear charge density is in fact equal to dq over dx. And it can be rewritten to say that dq is equal to lambda dx. So I can substitute lambda dx into my equation. Yeah. All right, and now let's pull some constants out of this integral, right? R is just the length to our spot. That's not changing. Linear charge density is not changing. Some constants on the bottom. So Ey is equal to I know that's not how I should write an improper integral, but just don't tell your math professor. So there we have it. If we can perform this integral, that'll be our answer. Now, this unfortunately requires trig substitution. I think that's the way I know how to do it. So most physics professors aren't going to make you do that. They might give you a table that just gives you the answer to this integral. I'll go ahead and do it just for, I don't know why. I'll do it in fast motion, so here I go. Okay, so I'm wondering if I missed an absolute value or something in my equation somewhere. I don't think I should have that negative sign, but it doesn't really matter because we know that really electric field is a vector, and we were just finding a component of that vector. So when we write our answer, it should probably be in vector notation. We already know that the direction of the electric field is going to be away from the wire, right? So depending on our coordinate system, we're gonna probably want to call that positive, basically. So that is our electric field at that location. Remember, we reasoned that by symmetry, the electric field only has a y component. So if I was to write it in unit vector notation, it would look like this. Let's see, that's the j hat. All right. So again, Gauss's law would do this in like 2 steps, and I'll do a video on that next probably. All right, bye.